Hi everyone, my name is Abel Siqueira and I'm starting a new series on JuliaSmoothOptimizers, which is an organization on GitHub for developing nonlinear optimization packages. The first tutorial we're going to have is the tutorial on the package LinearOperators.jl. So I have here a brand new notebook, a Jupyter notebook, and I'm using Julia 1.4.0. I'm gonna activate a brand new environment so we can all have the same packages. And I'm gonna be using the latest version of linear operators, which I think is 1. So let me just show that there is nothing here. 1.0.2, I think. So there's nothing here. I'm gonna add linear operators. Okay, I have linear operators 1.0.1. And also, since I know I'm gonna have to use graphics, I'm gonna add plots and GR, which is my favorite backend for plots. To have installed plots and GR, and for my test, I'm gonna use plots. I'm gonna set GR to an add page size plot something to make sure that it's working. This is precompiled and the first ran, so we should be all ready to go. We're gonna talk about linear operators, okay? So essentially, a linear operator is, in the package sense, it implements a linear operator in the linear algebra sense. What I mean by that is that instead of defining a matrix or either sparse matrix or element-wise matrix in some way, we're gonna define how a matrix behaves on a vector. So for instance, we can define the product of a matrix times a vector being v1 plus v2 and 2v1 plus 3v2. This should be the result of matrix 1, 1, 2, 3 being multiplied by a vector v1, v2. Okay, so we have this information, which is the product of a matrix, in this case implicit matrix 1, 1, 2, 3 by a vector v. And we're gonna define a linear operator through this operation here. So I'm gonna call it A because it will resemble a matrix. I'm gonna pass the sizes, so it has 2 by 2. And I know this matrix is not symmetric nor Hermitian, and it's defined by prod. Okay, so this is my definition. When I multiply A by 0.2, 0.5, I have, yeah, because I forgot to pass the type, as usual. Okay, so I have a linear operator defined by this product, and these work essentially the same as having the matrix 1, 1, 2, 3. Okay. In this case, I do not know what the transpose or the conjugate transpose of this matrix is, so I cannot simply infer that information. So in addition to having prod, I may also pass the transpose of this matrix, which will be something, in this case, which will be something like this. And I can pass this information, tprod and tprod. In this case, since I'm having a real matrix, I can ignore one of the arguments, which is for the conjugate transpose. But for full disclosure, I'm having everything here. Okay? So essentially what I'm saying is that a linear operator is defined by how it operates on a vector. It can be defined by only how it operates on a vector multiplied by the right hand side, but it can also be defined by the transposed or the Hermitian. I believe the notation can be improved a little bit. Let me write here, use here, okay, since we can do that. So these information should be passed to a linear operator, okay? In a simpler way, you can simply look at a matrix. For instance, rand 5, 2. I have this matrix, and I can define an operator through the matrix. And that's an operator. It will have the same number of rows as the matrix A. It will have the same number of columns as the matrix A. It will have the same type, and it should infer if the matrix is symmetric or Hermitian to its type. Okay. So an advantage of using linear operators instead of using the matrix directly is that, one, I can have lazy products. So if I have a 500 by, let's use a square matrix here, and I multiply C equals A times B, this operation should take 0.02 seconds. Of course, timing inside notebooks are not so, I'm not going to use benchmark tools now because I don't have it installed, so let's forget about it. Timing inside a notebook is a little bit wonky, but essentially what I'm doing is computing A transpose B. And if I have a linear operator of A and a linear operator of B, I should have something faster, okay? Very fast. Of course, then you're going to want to use these operators. So that's not exactly what we want to use. What we want to check, actually, what we want to check is how fast are these operations when I compute A times B times V. So this can be interpreted in two ways. And the same for the linear operator. So the first time I compute the product of A times B, it took 4 seconds. Now I have this information again. When I compute A times B first, it takes 4 seconds and some small additional time, which is not much. When I compute any other option, I have essentially the same result, okay? If I do not need the resulting matrix explicitly, I can define how the resulting matrix will operate on vectors. Essentially, what I'm saying is that this guy, OPA times OPB, is going to be the same as applying linear operators on A times B. But it will be much faster, okay? When you have an operator given by a matrix, for instance, rand 5, 2, and you create an operator through that matrix, this operator will work the same way a matrix would, while operating on vectors, of course. If I multiply this by a vector 2, this will be the same as multiplying the operator by a vector 2. And I also have the transposed in there, which is a special type, an adjoint type, which I can use for multiplying a transpose vector. So linear operators work very efficiently in that end. One use of linear operators can be, I'm gonna copy an example here. For fast Fourier transform, okay? So I'm just gonna copy this example of fast Fourier transform. Okay, FFTW is installed. Now I'm gonna define a linear operator 16 by 16, which is not symmetric nor Hermitian, defined by the functions FFT and IFFT. When I compute A times, let me define a vector V. When I compute A times V, I'm gonna have a resulting vector, which is equivalent to just applying the FFT on V. If I compute A times A transpose V, adjoint of A times V. So how do you say A adjoint? This is how you say. I think I ever a class algebra. Let's say the adjoint of A. So if you compute the adjoint of A times V, it's going to be the same as computing IFFT on V. So what I can do, for instance, is compute A transpose A times V. And this is going to be V. Okay. So these are times 10 to the minus 16 or 17. So this is very small. Okay. So we can check that A transpose A is close to the identity here. Let me see how I can write this a little bit better. Is approx. Yeah, in this case, I can write is approx. And here I'm gonna use is approx matrix. I have to use, I use I, does it understand sizes? So this is very close to the identity as well, okay? So a question here before I go on. Addition of linear operators, yes, you have. I still have OPB. I don't think so. So let me define linear operator, rand 33, OPB, linear operators. You have the sum, multiplication by scalar, minus 3 times OPB, works as well. Of course, I can do something like this. It understands most operations. I think I have a conj. Yep. I have a conj. I also have the adjoint of that conj, which is the transpose. So all that. So the adjoint of a an adjoint, let me say, transpose of an adjoint of the conjugate. So the main things are here, okay? So linear operators is the beginning of a lot of things, and one thing that is apparently strange is why do you have linear operators on these SmoothOptimizers organization? And the reason is that we are very concerned with large problems, and when dealing with large problems in optimization, we usually have, instead of having the Hessian of a function, the Hessian matrix, we usually have the product of that Hessian times a vector for large problems in optimization, for instance. So I'm gonna use forward diff here as an example. Suppose I have a matrix f of x, a function f of x, which is the Rosenbrock function. So using forward diff, I'm gonna define a function f of x. The gradient of this function is the gradient defined by f of x, and I would like to have the matrix Hessian, but instead of having the matrix, I'm gonna ask what's the result of x times a vector v, which in this case it could be defined. I'm gonna write this and I'm gonna remove. It could be defined as, so it's not autocompleting, never mind. It could be defined as the Hessian of f times v, but since I already have the gradient here, there's another way to define this. This is still not the most efficient way to define this, by the way. So there are other ways. It could be defined as the derivative of t going to the nabla of f plus t times v. F of x, nabla of f of x, and I'm gonna use ones and compute avhx. So this is working. How do we check if it's working? We compute the Hessian at the same point times v, and there is no Hessian of x, of course. There is a Hessian of f and then at x. So this is a way to define the product of the Hessian times v in a way that does not involve an explicit matrix. Is this efficient? No, this is just a simple way of showing how it works, okay? So for more efficient ways, we can look at our next tutorials on NLP models and derivatives, okay? So let's just assume this is good enough for now. So this is one example of how do I express the product of the Hessian times a vector. So this is it. I do not want to work with this all the time, so I could simply say I have an operator H, which is a linear operator with size 2, 2. It is real. It is symmetric and Hermitian, and only has one thing that we care. Okay? Notice that in this case, I have an x here, so this will be fixed at my current point. So instead of doing this, I can say OP, let's say OPX, and this is gonna return the value at x. I could say OPH at x, okay? This is better. So OPH will be OPH at x at this point x, and if I compute OPH times v, I'm gonna get the result. In addition to having this operator, I could define something a little bit more advanced. For instance, if this were possible, I'm not sure if it works for derivative, but I could implement this in some way that reuses the memory. So instead of computing this and returning the memory every time, I could compute this and reuse the memory, okay? So OPH times x is here. So a simple Newton method, while the norm of the gradient is greater than 10 to the minus 6. I want this direction to be the solution of the system h of x, d equals minus nabla f of x, and I'm gonna update x, okay? So I love Rosenbrock function because we can always do this and it will work, even though the problem will not be convex. So here I'm gonna use Krylov, which implements CG. Let me write conjugate gradient. More on future tutorials. And I'm gonna use Krylov.cg, and instead of passing the matrix, I'm gonna pass OPH and the nabla of f. OPH should be updated every time, which is OPH at X. And that's it. Let's just write this. No method matching, oh yeah, Krylov returns D and Krylov stats. Okay, so a very simple Newton method, or should I say factorization-free Newton method, in which I use the conjugate gradient method, an operator, so no explicit matrix is involved, and I have the solution with an iterative solver. Okay. Okay, so this is one of the main reasons that we have linear operators at JuliaSmoothOptimizers. It began when we were worried about how to solve this. Actually, Dominique was worried about this, how to solve these problems efficiently, and it actually started on Python. I don't know how many years ago. Okay, so a quick word on pre-allocated operators. So when I compute A times V, this is gonna create a new matrix that a new vector that I'm gonna use. In a situation like this, for instance, if I actually have an efficient implementation, the resulting vector D should be pre-allocated and reused every time. So there is a kind of operator that is the pre-allocated linear operator. I'm gonna show an example here, in which the allocation is made internally. This could be made externally, of course, so you do not have to use pre-allocated operator, but this saves a bit of time. So I'm gonna use this to pre-compile. I don't need to precompile because I'm gonna run this couple of times. No, I need to precompile. If I run it, in the same block. So this is how much memory is being allocated when I use OP1, which is the pre-allocated. By the way, maybe I should change this order so it's more makes a bit more sense to show the error first. So this is linear operator, and when I compute OP1 times V, I'm allocating 49,600, I think, bytes. And if I do this with OP2, we already saw the result, it is gonna allocate nothing. So the pre-allocated linear operator creates a vector for storing AV internally. So you should always remember this when you use a pre-allocated linear operator, or when you create a memory for yourself, of course. If you compute A times V, and then you compute A times W for another vector. So for instance, A1s is A times 1s. Forgot the sizes. And A2s is A times 2 times 1s. Okay. A1s is the same as A2s. So it's not the same, maybe. Because it's not A, of course, because it's OP2. Oh, that was scary. A1s is the same as A2s, okay? Because these are actually changes the internal memory. And changes. So this is essentially using the internal memory to store the result of OP2 times 1s. And this is changing that internal memory. So when I say A1s is equals to this is actually passing the reference to that vector, to that internal memory, and A2s as well. So this is why this triple equals is true, because they are the same object. Okay, these are pointers to a same object. So nothing stops the user from misusing linear operators. Okay, so for instance, if I define, I still have the prod here. No, let me copy the prod, which will be a good example. So you say prod and tprod. So you say prod is v1 squared plus v2 squared and v1 times v2. And tprod is the same as before. He doesn't know. He just, okay, I'll do it. Just goes ahead and use it. It assumes that you're telling the truth. It doesn't have any way of knowing that's not true. I can also have some special operators inside linear operators. There are some already defined, and we have plans to create new ones. One of these operators, I'm gonna define a matrix A times A plus I, so it's positive definite. I have OP inverse A, which is OPA inv. If I compute, let me define B equals A times once. I have OPA inv, which computes the inverse. I have OPHL, which is the Cholesky. So OPA inv and OPHL, here are OP inverse of A and OP Cholesky of A, which call the Cholesky decomposition and uses A backslash to solve a system. If I multiply, here multiply OP inv times B is gonna result on the solution of AX equals B, and OPH shall times B, the same thing here, okay? So I do not have this yet, but this is one of the projects that are interesting. I could define, for instance, approximate Cholesky. So how is the complete name? The incomplete Cholesky factorization. So I use only a little bit of the Cholesky factorization and define it as a preconditioner to a conjugate gradient solver, for instance. Okay, so we have that option here as well. So again, if I have Krylov.cg, let's define OPA. I like to give some spoilers on what's going to happen. So here I have the conjugate gradient. Here I have the number of iterations, essentially, that the conjugate gradient did, which is five iterations, the initial plus another 5, the starting value plus another 5, and I could pass OPHL. I could pass a preconditioner to Cholesky. In this case, the preconditioner is perfect, so there is only one iteration, which is the iteration to solve the system. This is to show that it is working as intended. Okay, so I have the inverse and Cholesky operators as well. I can define many things this way. Okay, so another operator that we have, which is also of interest to our JuliaSmoothOptimizers organization, is the BFGS operators. We have here BFGS factorization, which I'm not gonna present because it involves copying a lot of things. So I do have it open here in PDF, HTML actually. So I have B and H. I have to use a scaling equals false. Okay, I have B, which is an LBF-JS operator, and an H, which is an inverse LBF-JS operator. BF-JS is the kind of quasi-Newton approximation. L for limited, and inverse is the LBF-JS approximation, or the limited BF-JS approximation for the inverse of the Hessian. Okay, so this work, the starting BF-JS is just the identity matrix. Oh, sorry. It's just the identity matrix, but you can update it with a vector. This S should be the variation. Oh, that's good. Of X, and Y should be the variation on the gradient. By the way, it should be much easier to copy. Okay, so B is a linear operator. When I multiply B times 1 now, it changes. It's internally using only the vectors S and Y and the value of the inverse of the dot product of S and Y to form an efficient linear, efficient limited memory BF-JS operator. Okay, so as I said, these guys are inverse of one another. B times once each works as expected. Okay, and of course, as I did with the this method, I can do with a BF-JS. So here I still have the same f of x as above. So here, instead of op age, I could have age as an inverse LBF-JS operator, 2. And if I read correctly the question, can it just operate on vectors or also intervals? Just vectors. It doesn't have anything for intervals. It's just the traditional vector. LBF-JS can have longer history too. You can change mem to find here. For instance, I can have memory 2 or memory 5. I think the default is 5 or the size, whichever is lower. Because I can use 5 and it will be terrible. But yeah, I could have something like that. So here I have inverse BF-JS operator. I'm gonna ignore this, and instead of using Krylov, which I don't need anymore, I'm gonna use D equals minus H times nabla f of H. So this is gonna be a some direction. I'm gonna use only a small fraction of the direction because I don't want to make a line search here. Could I do a simple line search? I think I'm gonna do a simple line search because, well, otherwise we'll feel bad about this. So while not f plus t times v is less than f plus t times, I'm gonna use 10 to the minus 4 slope t divided by 2, and here I'm gonna update x. After updating x, s is t times d, and y is the gradient. I should store the gradient now. I try to avoid doing this efficiency, essentially, updates, so the code is shorter, but you can do them all. So here I'm gonna push into age as y, and I'm gonna create a counter here for the number of the number of iterations, I think, while not norm of g of x is less than this, or iter is more than 10,000. If I do more than 10,000 iterations, I have bigger worries. So I compute g of x here, which is updated here. X is updated here. Let's run this. LinearOperators LBF.js data mem equals to. Oh, I think I don't pass mem. I just pass 2. Is that it? Yeah. I don't pass the mem equals, just the value. And var and mem. So it ran in 0 iterations because I forgot to update. That's a very good tip for anyone implementing optimization methods. If you know the solution, any method is a great method. So 1, the solution, 10 to the minus 7, essentially the residual in 677 iterations. If I use only the gradient method, this is gonna take 10,000. So I know that I'm not doing the gradient method. If I change the memory to 1, it's gonna be a little worse. If I change the memory to 0, I'm not sure if it works because it's not made to have 0 memory. With 3, it's the same. So here we are testing it. I'm gonna use 1,000 in the memory. So even the BFJS non-limited works fine for Rosenbrock. Okay, not gonna leave this here so people judge me on that amount of memory. Cool. As I said, this is a cool use of an operator. You have the inverse LBFJS already implemented. Another use that we can have is instead of doing this kind of step control, we did a radius and computed Krylov.cg with h minus, I'm sorry, I'm gonna use b instead of h, b minus gx, and you can pass a radius here equals delta. And you're gonna have a truss region method using the LBF.js operator. Of course, this doesn't work the same way anymore, and you have to update the truss region here. So this is the hard part, of course, and gonna simply, yeah, this works. This is the hard part, updating the radius. I'm just gonna run and hope that it works. In this case, I believe it does. I just forgot to set the Krylov stats as output. So in this case, it did not work, so delta is too large. What I'm gonna do is slowly decrease delta. Oh, and I forgot to update age. So if I update age, if I update B, which is the LBF.js operator, each iteration, constant radius work. Oh, right. So this is one of the uses, these are two of the uses of the inverse LBFGS operator here, explicitly implementing LBFGS methods, one with the inverse LBFGS and one with the LBFGS operator. Okay, so this is another operator that we like a lot. Another example that I'm gonna define here just so I can show a cool application is one for heat equation. So this is gonna be in a tutorial, JSO tutorials. Let me check if it's online already. JSO tutorials. This is in this tutorial with details. Okay. So this is an application of heat equation. I'm going to consider I have a square plate with size L times L, and there is no heat exchange on the boundaries. So the heat equation is given by this. The variation of the temperature in time can be computed or can be defined as the Laplace operator at a specific point times the heat coefficient alpha. And the no heat exchange on the boundaries is defined by these derivatives in x and y at the boundary being equal to 0. Okay? So what we do in the discretization is that we approximate, first we create a grid, x1 to xm and y1 to ym, and we also discretize the time. And then we have I, j, and n for each step in this grid, for each point in this grid. And we're gonna approximate the derivatives according to these rules here. We're gonna use the forward scheme in time to approximate the derivative in time at the point n, y, j, using this forward difference. And the other differences are here. Okay, I'm not gonna go into details. If you take all these differences and you substitute in this equation at a specific xyt with indexes, you're gonna have this discretized equation. Okay, so this discretized equation you can rearrange to have it something like n+1, which is the next time step at the point yj, is gonna be given by this whole thing here, which is essentially saying that I had this value at the previous step, is gonna be decreased a little bit, and I'm gonna add all these things from the points surrounding my xi, yj. Okay. So I can write this linear operator in this way, which defines an update to each value u. Okay, so these are details for the boundaries, what happens. And in the end, we're going to have something like this matrix, which can be written as this matrix here. And each point u, each vector u, n, which is the whole linearized spatial values at n+1 can be simply defined by a times un. Okay, so this is a simple product of the previous vector times a. Remember, this is the linearized vector, so if I have 3 by 3 in the spatial domain, I discretized into 3 by 3 grid, I'm gonna have a vector with 9, which is the case, 9 values, okay, with dimension 9. So I implementing this here, you can see the details there, and I just implemented this. Essentially, it's a copy of what's online, you can check there. So I have the heat equation, these 4 values, the length, number of points on the grid, the time step, and the heat coefficient. And I define here first a linear operator for the tri-diagonal value here, which is the T, this tri-diagonal value T, tri-diagonal matrix T. So this is T prod. I define a linear operator with T, and then I define a prod, which is essentially defining how it operates on every other row. Okay, so I have T and 2G. I have T and 2D, which is the first line. Each other line is DTD, here DTD, and I have 2DT, which is the last line. Okay, so this is an operator. I compute here. I can spy the operator. I think I have to call sparse A. So I can use the spy to see how it works. How is this matrix? I made it here 3 by 3. I'm gonna change to say 10 by 10. I'm gonna have 100 elements. So this is not white, this is yellow. Okay, so this is yellow, and here there's a yellow strip as well, and the other values you can check with details online. Okay, so what I'm gonna do is define the heat equation at U0 Lm delta and alpha. I'm gonna compute this value, the first matrix. And here I'm defining what happens in the starting values, only that. So we can start our simulation. Okay, so say you have a heat equation that you want to solve, and you know that the starting value is something like 16 times x times 1 minus x times y times 1 minus y. You know the size of L. You know the size of your plate is gonna be L by L. I'm gonna use 1 here. I'm gonna use 10 points. I'm gonna use a time step of 0.1, and I'm gonna use an alpha of 0.1 as well. And what you're gonna have is UA equals heat equation of U0 Lm delta alpha. U is the starting value, and A is how you compute the next solution. I can simply say heat map is better. I'm gonna create a layout here. Plot layout. I'm gonna create a surface on the left, sorry, and the contour plots on the right. So this is my first example. Okay, so this is too small. I'm gonna use 100. And what I can do here is update U simply by saying A times U, and it's updated. Of course, it's breaking because I haven't really looked into the stability conditions of this problem, because I don't remember the conditions. This Maybe this is working because it's changing little by little. Okay, so I use the different point. Okay, so this is an advanced example which shows another thing that we handle, a larger way of writing things. I hope you have noticed that in the midst of all this, we wrote concatenated linear operators, something like this. One stands, this works. Also have the transposed of course you need the correct dimension, the transpose of the linear operators and everything like that. Okay. So if you look into the site, you can see that I completed with another example here, which was a little bit more interesting for the JuliaSmooth optimization organization. I create a function that is very specific for JuliaSmooth optimizers, which is our logo. And here's the starting condition, which is again our logo. And I compute this at different time steps. So with time equals 0, 1, 0, 2, and so forth. You can see that the initial heat is spreading. It's decreasing at the maximum values and increasing at the lowest values, of course. It has no heat exchange, so all the heat is contained. And here I have an animation of that happening. Okay, so all of this is done using only linear operators. So here I have u equals a times u, which is what's creating the animation. Okay. So this is it for my linear operators tutorial. I hope you liked it. Please leave comments asking for additional tutorials on Julia and optimization in Julia, and I'll see if we can make it. If you want to see live coding of Julia, please follow my Twitch channel and follow me on Twitter as well.